Welcome everybody to a new video on systems biology, digital twins and AI, and block 1 in TBMT42. So we have now reached the final part of block 1. We have learned how to formulate models, we have learned how to simulate models, and now we're going to analyze the models themselves from a mathematical point of view. And this is sort of without using data. It's just to analyze the models. And the key thing, the key component in such analysis is often to look at stability and other qualitative behaviors, because you don't know anything about the quantitative details because you haven't considered any data yet. And this is a field called nonlinear dynamics. And here we are in the first of 3 videos devoted to nonlinear dynamics, where we look at local stability and fixed points. So basically learning how to go from, let me change the pointer again, how to go from these type of curves to insights regarding stability and other qualitative properties. So from here to here, that's what we'll talk about in this video. So the first thing to learn is the difference between a transient and a steady state. In a steady state, we will learn why we can call that a fixed point, and we'll also learn the concept of a basin of attraction. So these are some central concepts that we'll need to learn to understand the more advanced concepts. So we have learned how to do these normal time plots, just simulations with time on the x-axis and starting at the initial condition x of 0. And if we do that here, and now all of these curves are just qualitative, so they are not actual simulations, because it's easier to illustrate in this way. So here we have one simulation starting here, and in red here we start at another place, but the same values of all the parameters, so the model is the same. And the green one we start at yet another place, and we see that for all of them we have a sort of tuning in phase, but for all of them we end up in the same place. And this is very, very common. And these two phases, the sort of tuning in phase, this is called the transient phase. And the place that you end up in, this is the steady state. And this steady state here is often called the fixed point. And why is it a point? Well, we need to go to another way of plotting things to understand that. And in this type of plot, we look at the phase plot where we have not time on the x-axis, but we have one of the states on the x-axis and another state on the y-axis. So here, time is not explicit, but it will be a sort of implicit parameter. So here we see similar type of simulations that we saw on the other one, but we see not only variations in x1, but also in x2. And actually, we need to look at all the states to know that this is really a steady state that we are looking at, because it could be that there is a contraction in some variables, but that one of the states is actually diverging. And then it's not a steady state or a fixed point. But here, we see that we go to something that is not sort of a straight line, but all of these curves here, the green curve and the red curve and the blue curve, they all come to the same point in space. And this point, this is called the fixed point. And here we also see that there are other simulations that end up in other points here. So you sort of have 2 parts of this phase plot that go to different fixed points. So here we have 2 fixed points, one up here and one down here, that are coexisting for the same parameters in the model. We have 2 fixed points. And if we separate out all of these curves and just look at the sort of the summary insight here, then we have these two fixed points that both are stable because you go to them if you start nearby. And then we have a sort of line here that separates. If you are below this line, then you will go to this fixed point. And if you're above this line, above this separatrix here, then you will go to the upper fixed point. And here, all the points that lie below this separatrix here is called to belong to the basin of attraction for this fixed point 1 here. And the points that are above this line here, they belong to the basin of attraction for fixed point 2. So all of these are central concepts that we need moving forward. So we have now understood the qualitative idea of a fixed point and of a stable fixed point. So let's formalize this a little bit. We won't dive super deep into all of the advanced mathematics, but the basics we need to know. So a fixed point is defined as a point in space for which the right-hand side, f of the ODE, if you, for the parameters that you're at, p, if you start there, the derivative is 0, meaning that if you start there, you will stay there. So that is the definition of a fixed point. If you start there, you will stay there. But in order for it to be a stable fixed point, then some further conditions need to be applied. And this is basically centered around something called the Jacobian, which is the derivative of f. So remember, f is a vector which has the right-hand side for all of the ODEs, all of the differential equations. And then you derive all of these with respect to each of the states. So the 1, 1 position will be the f1 dx1, and then the f1 dx2, and so on. So this is an n by n matrix, where n is the number of states. And a square matrix like this, you can calculate eigenvalues and eigenvectors. And these eigenvalues and eigenvectors, they tell us valuable information about the stability of this fixed point. In particular, all of the eigenvectors, they will point in different directions in the total phase state space, the space of all the x's. And in general, there are 3 subspaces that are spanned by these eigenvectors. The most common and most important one is the stable space. So this is the one where things are contracting and they are moving towards the fixed point. And this is spanned by those eigenvectors whose eigenvalues has a real part, so they might be complex numbers. So the real part of the eigenvalues has to be less than 0. So all of the eigenvectors that correspond to an eigenvalue where the real part is smaller than 0, they will locally converge exponentially towards the fixed point. So therefore they are called the center space. They span as a plane in the state space, which is contracting. And then you have possibly sometimes some directions that has a positive real part, and that is unstable. So there you will exponentially go away from the fixed point. And then you might also have somewhere where it's not positive, it's not negative, but it's actually absolutely 0. And this is a very particular type of situation where a fixed point has such eigenvectors. And the space that is spanned by those eigenvectors is called the center space. So here, by the explanation that I did already, you can probably already realize that if there is no unstable and no center space, then we have a stable fixed point, because the entire space, no matter in which direction you go, you will be contracting exponentially towards the fixed point if you are not too far away. But if there is an unstable space, there is at least one direction where you will diverge. And if you have a center space, then it's actually a non-hyperbolic point. And this is a very specific type of point which requires further analysis. And this is typically a bifurcation point. And we'll come to bifurcation in the next video. So let's just understand this thing by some plots. So an unstable fixed point, if you start there at the unstable fixed point and you simulate forward in time, you will just have a straight line. You will stay there. But if you start just a little bit away, then you will diverge, at least in certain directions. So you will not stay there. So if we again look in the phase plot, where we have x1 and x2 on the two axes, then no matter where we start, we might be contracting in certain directions. Those will correspond to the eigenvectors, which has a negative eigenvalue. But we will never really reach the fixed point if we don't start in it. But we will go close to it, possibly, and then we will start to diverge in certain directions. And these directions that we diverge in, those are the unstable directions corresponding to the eigenvectors with the positive real part of the eigen. So, final observation for this video. We do have other types of behaviors that might be stable as well. So here we see that we start at two different points, and we don't really seem to converge to a fixed point. We seem to sort of be stuck in this oscillation behavior here. And this is more clear if we look again in the phase plane, because then we will see that all of them go. So here you have the problem that you might have a phase shift, so you can't really see that it's exactly the same behavior. But here, time has disappeared, so you don't see the phase shift. So you only see where you go, and you see that all of them go to this green circle, or this sort of loop here. And this is called the limit cycle. And if this is stable, as it is here, then if you are a bit away from it, you will converge towards it. If you start close to it in the middle, or close to it, sufficiently close to it outside of it, you will converge to it. And then it's a stable limit cycle. And this is basically the sort of final observation for this first video, laying the basis. So a limit cycle is describing oscillations, and it's an example of something called a stationary behavior. So it's not a steady state behavior, because you're not stuck in one place, but you are stuck in a sort of behavior that you never get out of. And this stationary behavior can, for instance, be a limit cycle. So these are some of the initial concepts that we have needed to understand more advanced concepts that we will move on to in the next two videos.